Welcome to the electromagnetic theory and interference course. In this session, let us see about displacement current and how it is going to change the Maxwell equation. Let us see now. So last session we have discussed about one of the Maxwell equation, that is curl of the electrostatic field. Okay, we took that and we modified that for time varying conditions so as to satisfy the Faraday's law. Now we are going to reconsider another Maxwell curl equation, that is for a magnetic field based on Ampere circuit law. We are going to change it for time varying conditions. So for the static electromagnetic field, we know that del cross H is equal to J. If we take the divergence of a curl of any vector, it is going to be 0. So applying the same in above equation, del cross H is equal to 0. I am applying the divergence to the both the side of equation. So del dot J. Actually, due to continuity of current, the del dot J is not equal to 0. It is a rate of change of volume charge density minus dou rho V by dou T. Actually, these two equations are not compatible for time vary conditions. So we are going to modify this equation del cross H is equal to J by adding a one more term called JD. That JD is called the displacement current density. And after adding that JD term, we are going to again apply the identity, that is the divergence of curl of a vector is 0. So this right hand side also del dot divergence we are applying. Okay, and for this equation, this particular 9.21 equation, to agree with this equation, what should happen? That del dot JD, it should be equal to what? If I take this term, it is minus del dot J. So we already know del dot J equal to minus dou rho V by dou T, but already one negative sign is here, so it's here positive only. We know from Gauss law for a magnetostatic electrostatic field that del dot D is equal to rho V. So instead of rho V, I am going to write del dot D, and I am just going to interchange the divergence and the partial differentiation. So del dot dou D by dou T. If I compare the first and the last part of this equation, it is neglecting the divergence, it is JD is equal to dou D by dou T. So I have found this displacement current density, and I am going to add this in this equation. So this is going to be my Maxwell equation based on the Ampere circuit law for time varying case. Okay, where JD is equal to this dou D by dou T is called displacement current density, and this J is called conduction current density, which is equal to conductivity times electric field intensity, sigma, right? And this was the JD is added by the Maxwell, because without JD term the propagation of electromagnetic waves will not be possible. And to find the displacement current, we need to take the surface integral of the displacement current density JD. Okay, and that is I can equate to, since J we have found as dou D by dou T, right? JD is dou D by dou T, and I am applying here. So displacement current is the result of the time varying electric field. So D equal to epsilon E, right? So it's due to time varying electric field, and you can see the displacement current when through a capacitor when alternating voltage source is applied to its plates. So now let us see the final form of Maxwell equation. Okay, that is for time varying conditions, right? So we can observe that the divergence equations remains the same while the curl equations are getting modified here. Integral form we will understand its physical law, whereas the differential form we will use most frequently in solving the problems. For a field to qualify as an electromagnetic field, it should satisfy all the four Maxwell equations. We already know these two from the static case, but time varying case, instead of del cross E is equal to 0, it is minus dou V by dou T because of the Faraday's law. Similarly, del cross H does not visa, it is not only J, it is one more term is added, that is JD, that is dou D by dou T. This is based on Ampere circuit law. And we know how to write in integral form, we discussed in the previous session, right? Now let us solve one problem based on this problem. A parallel plate capacitor is given whose plate area is 5 cm square and the plate separation is 3 mm. And to the capacitor, AC voltage is applied 50 sine 10 cube T volt, and we are asked to find the displacement current, assuming the permittivity is twice that of free space permittivity. We are asked to find ID, right? Displacement current, that is equal to, we know it is displacement current density into surface area. So the JD term is not given directly here. So we need to find, we already know JD equal to dou D by dou T, right? What is D actually? D is equal to epsilon E. And we already know one more relation, E is equal to voltage applied by the distance, V by D. So I am applying the same in this JD term. Epsilon is common, constant, D is constant, only the voltage is time dependent parameter, so dV by dt. And here I have to multiply the surface area, right, with this JD term. So extra s I have written. So I'm just going to substitute all the given data. 2 times epsilon naught we already know, right? 8.854 into 10 power minus 12 farad per meter. So we can apply that, and this is one more approximation they have given in 10 power minus 9 divided by 36 pi. And here surface area we know it is 5 centimeters square. So centimeter means 10 power minus 2. That whole square is 10 power minus 4. And D is going to be 3 millimeters. So 3 into 10 power minus 3. Okay. And here for this voltage it is 50 into, okay, sine 10 cube T volt. They have to differentiate with respect to T. Differentiation of this constant, right? 50, I am taking it constant. Sine differentiation is cos 10 cube T into 10 cube will come before. So if I simplify this, I will get the answer in nano ampere. I hope you understood. Thank you, everyone.